Area under this particular graph will give you the previous quantity, that is displacement. If you find out the area of the triangle and the rectangle, you can add them together and then you will get the total area, right? Now, if you remember a few minutes backwards, we already proved one first equation of motion. Area under the velocity time graph will give you displacement. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with motion in a straight line. And in this class, we will be looking at equations of motion. That is, we learned about how the graphical setting works. Now we'll be diving into a more theoretical background, that is, equations of motion. So let's dive into it without further ado. So there are several equations of motion which connect various quantities with each other. That is, if I have a particular graph like this, let's say this graph is, this is the nature of the velocity time graph, which means that some object is starting with a non-zero velocity. That is, when I start that particular object, that is, if I am firing a bullet or if I am throwing something which already has some motion, that is, something is moving and I just gave it a push. I saw some bird flying like this, I got irritated and I started giving it a push and it moved a little bit more, which means initially it was not having the velocity factor as 0. That is, it did not start from rest. So 0, this is V and this is T. So this is a velocity time graph and it is having a non-zero initial velocity. Let's say here in this particular case, I'm taking U as the initial velocity, and let's say that this particular final value, let it be V. So it started with an initial velocity U and finally it had a velocity of V. Remember, this is not abruptly ending here. I'm just using this for explaining purposes. So the graph is increasing steadily upwards, but for our case, I'm only taking a small portion till here. So what is exactly happening here? There is an object which is having an initial velocity. It is moving with a uniform increase in velocity. So we can say that in this particular point where the graph is ending, I can say it is having a velocity of capital V, or simply the final velocity is V. So if initial velocity is equal to U, let's say vector U, and final velocity is equal to vector V, then all this can be interrelated. That is, there is an innate relation between time flowing through the initial and final velocities. We can find a relation between or amongst these quantities and mathematically write them down. So these mathematical relations between the different quantities is known as equations of motion. In this particular case, we are going to derive the first equation of motion. So we are going to derive the first equation of motion. It is very simple. You don't have to worry about anything. We are not bringing in any new quantities. The only thing we are going to do is that we are going to find out what is acceleration. We already know from the graphical methods how we can find out what acceleration is. You don't have to worry about anything. We do know that the slope will give you the acceleration. That is, if I take a particular slope here, then we know that del y by del x is equal to slope, which means that particular slope, here it is velocity time graph, so that particular slope will give you acceleration. So you don't have to do anything. You only have to consider the slope, and we can write that as del y by del x, which is equal to y2 minus y1 divided by x2 minus x1. In this particular case, it is y2, that is final velocity v minus u divided by t2 minus t1, or simply here it is, let's say t2 minus t1. So here I am taking the bigger triangle. Here I am taking the bigger triangle, not a little triangle, so the calculations are easier. So I am taking this particular slope. So The starting point of t is actually 0 and the final point is here, let's say it is t. So the final point is t and the initial point is 0. So we can say it is t minus 0, or simply it is v minus u divided by t, which is equal to acceleration. Or simply we can write this a bit more neatly, and we can say that at, that is, I'm taking this t here. There is no problem, right? I multiply both sides by t. So this gets cancelled and a t gets added here. So not added, multiplied here. So at is equal to v minus u, or simply I'm taking this u to the left hand side, that is adding u on both sides. Then you get u plus at is equal to v, or simply we can say that the first equation of motion is v is equal to u plus at. This is the first equation of motion, which is very important for you guys. So we used a graph, that is, an object is moving with an initial velocity and it had a final velocity. We took down that graph, that is velocity time graph, and we noticed that it had an initial and final velocity. Then we solved the slope equation, that is, we found out what was the slope of that particular graph. Slope is acceleration, and we rearranged that particular equation until we got a standard form. So v is equal to u plus at. That is the first equation of motion. Now, are we done with just one graph and one equation? No. Okay, it might be too hard for you, so I'll just use the same graph throughout to derive the three equations of motion. That's it. We have three equations of motion. So to derive that, I'll use the same graph, and the graphical method will be much more easier for you to understand. That is why I'm using the graphical method here. So anyways, I'll use the graphical method to derive the three equations of motion. So we are going to focus on the second equation of motion. So we are going to find out what is the second equation of motion. Here again, we are going to use something we learned in the graphical method, that is area under velocity time graph will give you, that is u, displacement. Remember when I told you that area under the graph will give you the previous quantity. That is, in this particular case, it is a velocity time graph. Area under this particular graph will give you the previous quantity, that is displacement. Slope will give you the very next quantity, that is acceleration. So here, area will give you displacement. So what are we going to find out here? Displacement. So we are going to calculate the area under that particular graph, and we are going to find out what is an equation for displacement will look like. So I'm going to find out the area under that particular graph. And now, how do we find out that particular area? Okay, sir, I don't know what this particular shape is, so I don't know what is the area. It's okay. So first, let's take it slow. There is a triangle here, there is a rectangle here. If you find out the area of the triangle and the rectangle, you can add them together and then you will get the total area, right? So let's start from there and then slowly find out what is the area of this entire thing. So there are two regions here, region 1 and region 2. So there is a triangle and a rectangle here. So area under the graph will be equal to area of the triangle plus area of rectangle. I have very bad handwriting, please bear with me. So area of triangle plus area of rectangle will give you the total area under that particular graph. So we do know what is area of a triangle. Area of a triangle is equal to half base into height. If you don't know that, I don't know how you passed high school. And area of a rectangle is equal to length into breadth. If you don't know that, you should not even be in a science stream. So our objective is to find out now what is half BH and what is length into breadth. So we need to know what is breadth, what is length. We need to know what is base, what is height. So luckily we have a graph here and we have the necessity quantities to analyze and give us the required details. For example, here the base and the length of the rectangle is same. That is, the base of the triangle and the length of the rectangle are both same, and that is T. So 0 to T is the length here, or 0 to T is the length or base of that particular triangle also. So we have the base and we have the length. Now we need to know what is the height and what is the breadth. So again, breadth here is nothing but u minus 0. So here it is the breadth is u minus 0, which is nothing but u. So it is having a breadth of u, and here for the triangle, what is the height? The height is from here to here, that is v minus u. Higher value minus the lower value will give you the actual height of that particular triangle. So in this particular case, it is v minus u. That is, if this is 5 and this is 10, the height will be 10 minus 5, 5. Just like that, here the height will be v minus u. So we have the height, the base, the length and the breadth. The only thing left to do is substitute everything into this particular equation. So area under that graph will be given by adding the area of the triangle and the area of the rectangle. And simply we do know what is the equation for finding out the area of the triangle and the area of the rectangle, and we know what are the values to be substituted. So that values will be substituted in this particular equation, and voila, comes out the answer. So it is actually half base. Base is nothing but T. So half T into height. Height is nothing but v minus u. So height is nothing but v minus u plus length into breadth. Length again, it is breadth. Breadth is nothing but u. So we can rearrange this equation. I can write it as half v minus u into t plus ut. But this doesn't look so good because there is 2 terms of initial velocity, 2 terms of time. It is not looking that good. So I'm going to rearrange this equation a little bit. That is, here I have a v minus u. Now, if you remember a few minutes backwards, we already proved one first equation of motion. So that particular equation was u plus at. That is, if you look here, then we know that v is equal to u plus at, or simply v minus u. That is, v minus u is equal to a into t. So v minus u is equal to a into t. That means we already have a v minus u here. So we can substitute that particular result in this form. That is, we have from first equation of motion, we know that v minus u is equal to at. V minus u is equal to at. Or you can start from v is equal to u plus at and rearrange it until you get v minus u is equal to at. And then we are going to substitute that particular result here, and then we will get implies half, instead of v minus u we will write at. Half at into t, that is at square plus ut will give you what? The area. And what is the area under that particular graph getting? Displacement. So here I am going to indicate displacement by using the letter S. So I can write S as the displacement. So I am going to write S is equal to ut plus half at square. I just rearranged this equation. I took ut first and half at square last. So ut plus half at square. So the second equation of motion is displacement is equal to ut, that is initial velocity times time, plus half acceleration times time squared, ut plus half at squared. So this is the second equation of motion. Are we done? No, we just have one more thing to find out, that is the third equation of motion. We will be using the same graph and we will be finding out the third equation of motion. So the third equation of motion is quite frankly very simple. So here I'm not going to take the entire graph, I'm just going to take the shape of that particular graph. That is, we had the graph like this, right? We had an initial velocity and a final velocity, and the shape of the graph, if I take just the shape, it is like this. I have a base like this and two lines. One line is a bit longer than the other, but they are parallel to each other. So I have two parallel lines and a roof like this. So this particular shape, that is this particular shape is known as a trapezoid. That is, it will have a triangle on top and a rectangle sitting below that, a square or a rectangle sitting below that. So this particular shape is known as a trapezoid. And I told you before, the area under the velocity time graph, that is, the area under the velocity time graph will give you displacement. So in order to find out displacement, it is not just one method, that is adding the area of triangle and rectangle. You can also use the direct equation to find out what is the area under this trapezoid, and then you will get the displacement equation, or simply an equation to find out displacement. But here we are not actually using this to find out what is displacement. I'll tell you why this three methods are there and three equations are there. But yeah, so how do we find out the area of this particular trapezoid? So the area of this particular trapezoid is found out by a simple method. So there are two sides, let's say A and B. There are two sides A and B, and they are parallel to each other. So these are two parallel lines. One is a bit longer, one is a bit shorter, but they are parallel lines. And the equation to find out the area of the trapezoid is area of, let's say, trapezium. So trapezium, area of trapezium is actually given by the equation A plus B divided by 2 into its base. That is, this is the base. Let's say this is H. It can be anything. Let's say it is H. Then I can write it is A plus B divided by 2 into H. So it is A plus B divided by 2 into H. That will give you the area of that particular trapezium. The area inside this particular shape is given by this particular equation also. You can also use half BH plus L into B, but that is one method of finding it. This is another method of finding it, which will give us a new equation. So why do we need a new equation? We actually need it because of a certain thing. That thing I'll explain it to you at the very last session. That is, the very last point of this class, I'll tell you why we need that particular set of equations. Now we do know that this is A, this is B, and this is H, which means here we have initial velocity U and here we have final velocity V. We are just using the previous graph itself. That is why I'm not again and again drawing the same thing, but just know that this is a velocity time graph and we have final velocity V and initial velocity U. So we have initial velocity U and final velocity V, and this is the nature of the graph. Now we have to find the area of this trapezium or trapezoid. So area is actually given by, area will be equal to displacement, and that is actually equal to A plus B. A is nothing but this side. So if this is 0, U minus 0, so U is A plus B. B is nothing but this particular side, and you know this particular length is actually equal to this particular length, that is 0 to U, which means, 0 to V. So this particular length is nothing but V. So it is actually U plus V divided by 2 into h. H was nothing but distance from here to here. And we already know that particular distance, it is t. So now it is just a matter of simplification and a minor substitution. So it is u plus v divided by 2 into t. That will give you displacement. That is the area under that particular graph. Again, I am not liking the way that particular graph is sitting. So what I'm going to do is that I'm going to consider the first equation of motion again. That is, from first equation of motion, I'm going to write that I don't like t, so I'm going to find a substitution for t. So we know v is equal to u plus at. That means v minus u divided by a is equal to t from the first equation of motion. So I'm going to write s is equal to v plus u. I'm going to write this half here. So v plus u into v minus u divided by a. Let it not be confusing. So v plus u by 2 into v minus u by a. So if you look very closely in the numerator, it is v plus u into v minus u. Or simply, so you might actually remember this dude, that is a plus b into a minus b, which will be equal to a square minus b square. So in this particular case, it is v and u, so I'm going to write it as v square minus u square by 2a. This is a multiplication, so I don't have to write 2 and into a, so it is just 2a. So v square minus u square by 2a is equal to s, or simply displacement can be found out using this particular equation, which I'm going to rearrange. I'm going to take this 2a into this side, so it is 2as. So 2as is equal to v square minus u square. If I take that u square also to the side, I can rearrange and write this equation as v square is equal to u square plus 2as. So this is the third equation of motion. Now, the important question, why do we need these three equations of motion? The reason why we need these three equations of motion is because each of these quantities are related in such a manner that it is independent of just one quantity. That is, if you look at the first equation, v is equal to u plus at, then you can see that there is initial velocity, final velocity, acceleration and time. But when we look at the second equation of motion, there is displacement, there is initial velocity, there is acceleration, there is time. So in order to find out displacement and in order to avoid final velocity, we can actually use this particular equation. If we have initial and final velocities, then we can use this particular equation to determine the acceleration or time or whatever we can find out. But if we want to find out the displacement, that is, you might have seen in movies that the hero will go to a cliff or will be inside a cave or something, and he wants to know what is the depth of that particular cave or what is the depth of that particular well he wants to climb into. So what he'll do is that he'll randomly take a rock and drop it down, and he'll watch his watch and measure the time taken. Okay, in 3 seconds, I heard the rock hitting the bottom. I heard the clink sound. So what is he actually doing? He's actually using this particular equation in order to measure the displacement, the vertical displacement. That is, if he's holding the rock like this initially, the initial velocity is 0, which means this whole term is 0. Only thing remaining, half at square. When I drop the rock is falling under the influence of gravity, which means automatically A becomes g, acceleration due to gravity, which the value we know, it is a constant, that is 9.8 meter per second square. 9.81 if you want to be accurate. So, but anyways, so we know g value. The only thing remaining is time. That is why he has his watch. So let's say in approximately 3 seconds, that rock reached the bottom, which means 3 square. 3 square into 9.8 divided by 2. So 9 into 9.8 divided by 2. let's approximate acceleration due to gravity to be 10, then 90 by 2, 45. So it is actually 45 feet or 45 meters or 45 kilometers, depends. That much distance it will be down. So generally we can say we are using SI units. So it means that it is going to be 45 meters long or 45 meters deep. Just like that, we can use the equations of motion to find out the unknown quantity just like this. This is just an example for that. And finally, the final equation is absolutely independent of time. There is no term of time here. It is only displacement, acceleration, initial and final velocities. It is completely void of time. So each of these three equations are versatile on their own. So that is why we are studying them and understanding them. So again, the way we find out the first equation of motion is that we consider the graph where there is an initial and final velocity. It is a velocity against time graph, and then we will take the slope, and when we take the slope, we will have the first equation of motion. And for the second equation of motion, it is very simple. We are going to exploit a rule or just property of graphs, that is area under the graph. In this particular case, it is velocity time graph. So area under the velocity time graph will give you the displacement. So in order to find out the displacement, I'm going to take the area of the triangle and the rectangle separately and add them together. So when I add them together, in pops out the equation of displacement or the second equation of motion. And finally, for the third equation of motion, what I'm going to do is that the same graph, I'm taking this particular shape, and that particular shape is that of a trapezium or trapezoid. So we can say that the area of that particular trapezium is given by a plus b by 2 into h. H is the base height here. So we can say, rearranging that particular equation and substituting from the first equation of motion, we arrive at v square is equal to u square plus 2as. So these are the three equations of motion. Questions can be asked in a variety of different ways, but generally you only have to pick out the individual terms, that is velocity or acceleration or displacement, and then you only have to substitute the values, and we have a use for that. So I hope you have understood about all the three equations of motions, and it is a very easy chapter. And I'll see you all with the new chapter in the next class. Until then, thank you.